Good morning, sir. I'm Lokesh from AML B section, carrying the pin number 259558610 So my topic for this Tech Talk video is design and analysis of radix sort for spare data in memory contained systems, constraint system. So, understanding radix sort. What is a radix sort? Radix sort is a non-comparative sorting algorithm that sorts numbers digit by digit, starting from a least or most significant digit. So, least significant digit contains the in the array element the last, and most significant digit is the first one. So, it works efficiently on integers and strings, typically with order of n into k. So time complexity, whereas n is the number of elements and k is the number of bits or digits. So however, in memory constrained systems like embedded devices, and when data is spare, uh, many empty or zero entries, the space is a zero entries. The traditional radix sort consumers more number of decides. Here the problem. What's the main problem? So space data has a large range of possible values, but a few actual entries. So regular radix sort creates buckets for all impossible digits or values, wasting memory. So systems with a limited RAM of IoT devices, mobile hardware cannot afford this memory overhead. So the main objective in this spare radix sort is to design a memory efficient radix sort that handles the spare data efficiently and uses a minimal additional memory, and maintains a sorting speed and accuracy comparable to a standard radix sort. So here the standard later on explain the latter standard radix sort. So the design approach, dynamic bucket allocations creates a bucket only for the digits that actually appear, not all possible values, and compressed data represents uses hash maps or single linked list structural programming for arrays. The adaptive radix sort, radix width. Choose a smaller radix basis. Example 2 power 4 equals to 16 based on available memory. In place sorting. Minimize auxiliary space by performing sorting within the original array. Streaming or block processing. Sort data in kernels when entire data set cannot fit the memory. Here, this radix sort is the standard radix sort. How the radix sort works and how it divides. The first we take some elements. In the elements, we connect the first significant bit, and we divide all the elements by 2, and we divide all the elements into two parts. In that two parts, we divide one part into again two parts. Uh, Later on, we go in dividing, and at last we connect the two divided parts again. This also called as a divide and conquer method. Here, this is the standard radix sort. So the main analysis is metrics, traditional radix sort, and the spare optimizing version. What is this? So when the time complexity when this has the time complexity order of n into k, the traditional radix sort has the order of n into k, whereas compared to spared optimized version, it has same say order of n into k. In space complexity, we have order of n plus r. R is the radix sort theorem. And next, here the spare optimized version, order of n plus b. Whereas b is less than r, it has one shift before r because it is the space is much lower than normal radix sort, because the normal radix sort wastes more space connected to this. Then the cache memory efficiency is a moderate here in a normal radix sort and improved in spare optimized version because the memory in a background must like it should not hold more. If it's more, the space complexity increases and the program maybe lag and the like this. The improved version has no cache. I cannot say no cache memory. It has a less cache memory compared to Radix sort. It is suitable then normal Radix sort is suitable for dense data and spare. This is suitable for low memory systems like mobile phones, etc. etc. In PCs, we can develop a standard Radix sort, whereas in normal mobile phones or else low memorized, low RAM, we cannot use this standard Radix sort in all versions. So here the main we can conclude that like the optimizer Radix sort for sparse memory limited systems. Here reduces unnecessary bucket allocations, improves memory utilizations, maintains sorting efficiently, and the ideal resource sorry and the ideal for resource contains AI embedded IoT environments. Here, how the main point is so how the memory is limited for radix for space sort. How it is limited. I have already told you that dynamic bucket allocation. From these dynamic bucket allocation, the like I can say that the memory is limited because it can there are the static standard radix sort has more memory. In this we use dynamic bucket allocation. The dynamic bucket allocation means it creates a bucket only for the digits that appears, not for the all digits. In standard application, it can create for the all digits. In compressed data representation, it uses hash maps. Hash maps concept is nothing. It's a very normal thing that hash map concepts that we have to specify the data type integers, a less than symbol, hash map, and a greater than symbol. We can give the data elements like a character, value, key, and its value. This is a hash map concept. In this, it doesn't take much memory because we can have a specific one. We can give only the specific values for it. And adaptive radix width, the width for the smaller like we are using this in a small rammed, so we have to choose a smaller radix width. Here we took as example of 2 power 4 radix width, and there is a block processing in this, like sort data in conch when entire data set cannot fit in the memory, and like it blocks some process, it blocks some digits for certain time, and it releases it blocks some and it releases this teaming process is known as block processing. So this is the conclusion for this optimizer radix sort for space. It has a memory limited systems. Thank you, sir.